Good morning. My name is Ira Mark Egdahl, and today's topic is time travel and the fact that we actually do it all the time. You can find out more by going to marxmodernphysics.com. Brian Greene, the best-selling author and physicist, tells us that time is amongst the most familiar yet least understood concepts that humanity has ever encountered. And today we'll talk about a particular aspect of time discovered by Albert Einstein. Time machines are a favorite ploy in science fiction stories. You climb into one, set the dials, press the button, and zap! You disappear into another century. A real possibility? Well, physicists are not sure. But one thing that most people don't realize is that time travel is actually a common, everyday experience. And you don't need a time machine to do it. It all is based on a core tenet of Einstein's theory of special relativity called time dilation. In Einstein's crazy world, time is not rigid. Time does not go by at the same rate for everyone. Now let's take a look at the impact of this amazing discovery. Imagine that I am moving at an everyday speed with respect to you. Say, for example, we both have super accurate watches on and they're identical. And I walk across the room with respect to you. Now, because I am in motion right now, my watch is running a tiny, tiny bit slower than your watch. Now imagine if I somehow were able to speed by you at 87% the speed of light. What Einstein tells us is that the faster we move, the more this effect occurs. And at speeds approaching the speed of light, the effect becomes dramatic. So if I am moving by you at 87% the speed of light, Einstein's formula tells us that my watch is now running at half the rate of your watch. For every second, what that means is that for every second that ticks off on your watch, only a half second ticks off on my watch. Say, for example, we had super accurate stopwatches, and I traveled around for a while at 87% the speed of light, and then we got together and compared our speeds, compared our times. Your stopwatch shows that 1 hour has gone by. But my stopwatch, because I am moving at 87% the speed of light, shows that only 30 minutes have elapsed. Hard to believe? It does sound crazy. We can only imagine how Einstein must have felt when he first thought of it. It took tremendous guts for him just to propose such a thing. Time does slow down with motion. How do we know this? Because we have evidence, supporting evidence to show that. For example, in October 1971, Joseph Hafele and Richard Keating put atomic clocks on airplanes and flew them around the world and kept identical atomic clocks on the ground. And they showed that the clocks, in fact, do slow down with motion. And of course, per Einstein's general relativity, are affected by gravity. They showed for their experiments that Einstein's time dilation agreed to their data to about 10%. In June of 1976, Robert Vesset and Mark Levine put super accurate hydrogen maser atomic clocks on Scout rocket and left one on the ground. And when they compared the two, they found that time does slow down with motion, agreeing with Einstein's formula to 70 parts per million, an incredible accuracy. We also have evidence for time dilation with our global positioning satellites, which tell us our locations on the Earth. In fact, GPS provides a continuous verification of Einstein's prediction that time is slowed by motion and by gravity. GPS would simply not work if it didn't take into account these predictions by Albert Einstein. And there is a number of laboratory experiments over the years that have also verified that time dilation is in fact true. For example, in 1992 at the University at Colorado State University, time dilation was verified to an incredible 3 parts per million. So what does this tell us? It tells us that time is relative. Time does slow down with motion, and in fact, just the amount predicted by Einstein's formula. So Einstein's crazy universe is our universe. Okay, what does this have to do with time travel? Let's take a look. Imagine it is the year 2950, and you have just purchased your brand new hot rocket car capable of speeds approaching the speed of light. So you travel into outer space to a distant star at 87% the speed of light. And time for you passes at half the rate of time on Earth because of your great motion. Now say the trip takes you 5 years round trip to go to the star and return back to the Earth. So what you do is, every 24 hours on your clock, you mark off a day on your calendar. And every 365 and a quarter days, you mark off a year. When you return to Earth, you find that your calendar tells you it is the year 2955. And in fact, 5 years have passed in your rocket. You have only aged 5 years. But here on good old Earth, time is not running slow like in your rocket. So when you return, 10 years have elapsed on Earth. In fact, everyone on Earth has aged 10 years, and Earth calendars now say it is the year 2960. When you alight from your rocket car and step into solid ground, to you it is the year 2955. After all, you've only been away 5 years. But it is now the year 2960 on Earth. So you have been away 5 years, but you've come back to the Earth 10 years later. So in effect, you have traveled 5 years into the future. Okay, for special relativity, in principle, if you traveled fast enough, you could arrive back on Earth thousands of years into the future. Let's say you took a round-trip from Earth to a very, very distant star at an incredible speed of 99.99999% the speed of light. You leave the Earth, you travel across space at that tremendous speed, you return at that same speed, you return to Earth. Now you have been away 1 year, but what you find when you return, it is 2,236 years later on the Earth. You have in effect traveled in 1 year, thousands of years into the future. So, per special relativity, you can and do travel into the future, but it is a one-way ticket. You can travel into the future, but according to special relativity, you cannot travel back into the past. Now let's look at everyday time travel. Imagine that you leave for work in the morning and your roommate is home sick in bed at rest, and your roommate stays at rest the entire day. You drive to work, go into your office. At the end of the day, you go back into your car and drive home. When you return from work in the evening, you find that because of your motion to and from work, and any other motion that you have experienced during your workday, time for you has run a tiny bit slower than time for your roommate lying at rest in the bed. So you have, in effect, traveled a tiny bit into the future. Now, the point here is that any time you're in motion, you experience this effect. In fact, every time you leave a place, the slowing of time due to your relative motion means that you return to that same place a tiny fraction of a second into the future. So what does this mean? Drum roll here. We are all time travelers. Thank you very much.